So this week we're excited to have Yuan Yao from UC Berkeley. He's going to be calculating the ECH gluing coefficient for a pair of pants covering a trivial cylinder. And based on his shared iPad screen, I'm going to say that the obstruction vanishes in that case.
Okay.
Go ahead and take it away.
Okay. So the coefficient's 1, by the way. Yeah. So this talk, I'll just kind of set up some of the, give some indication of how the analysis goes to show the obstruction actually vanishes. I'll do it only in the simple case for the pair of pants. And so the outline, I'll first give a recap of ECH and why we need to glue. And then I'll set up the gluing, and then we'll think really hard about the obstruction bundle, the obstruction section. So I don't know how long this talk is. Hopefully it will neither be too long or too short, but we'll see. So recall that ECH counts ECH index curves between ECH generators, which are collections of Rabe orbits. And the ECH index 1 condition is a topological condition. And in particular, it will impose some partition conditions on the endpoints. So what this means is that if you have a simple Rabe orbit gamma, then an ECH index curve can only approach gamma along in certain ways. They have to obey the ECH partition conditions. So in the specific case we're interested in, let gamma be an elliptic Rabe orbit with rotation angle that's very close to 0, but greater than 0. So if you have an ECH index 1 curve that wants to approach gamma with total multiplicity 2, so it wants to hit gamma with twice, the only way it can do that is if it had a single end with total multiplicity 2, and it wants to approach gamma from as s goes to minus infinity. The only way it can do that, as imposed by the ECH partition conditions, if it had a single coming in and coming in and covering gamma as a. Similarly, if U minus is an index 1 J holomorphic curve that wants to approach gamma with total multiplicity 2 in its positive end, then the only way it can do that is to have two ends approach gamma, each with covering multiplicity 1, as I've drawn here. So this creates a problem. So notice that they approach gamma in different ways. And this creates a problem for us if we want to show d squared equal to 0 in ECH. So why is that? Recall that d squared equals 0 is basically counting some kind of two ECH index 1 curves stacked on top of each other. That's kind of what the differential squared counts. And the usual way of showing d squared equals 0 is to show that this configuration belongs to the boundary of some higher dimensional moduli space. So, and then the one dimensional moduli space has even number of ends, and therefore it's 0. And the way we usually show that it has it's the boundary of a higher dimensional moduli space is to glue these two things together at the ends. But here, we can't really do that directly because this one comes in as a double cover of gamma, and this end comes in as two single covers of gamma. So the way to do that, so that's kind of here as a double cover, and here as two single covers. So the solution in this case is to glue in a branch cover of a trivial cylinder to make the ends match up. In this case, a pair of pants. So I'm going to insert in the middle level a pair of pants. Over here, it's a double cover of gamma that matches up with this end here. And here are two simple covers of gamma that matches up with the ends here. And here, and in this particular case, we will be able to glue along a pair of pants. Okay, so let me say something about the gluing setup. So we'll only work in this, basically in the case where I've drawn the above picture, we'll only work in a simplified setup of a gamma with an elliptic Rabe orbit of rotation angle close to 0. And U plus only approaches gamma with it approaches gamma and only approaches gamma with multiplicity 2 as s goes to minus infinity. And U minus approaches gamma with multiplicity 1, 1. So as 2 simple covers as s goes to plus infinity. And gamma is a pair of pants. And just a slight technical side remark, we'll be gluing as, we'll be viewing all of these things as J holomorphic submanifolds. So we'll later on when we talk about their deformations, they'll be in a normal bundle. Okay, so that is kind of the schematic for the gluing. So of course, the issue here is that there's a branch cover of trivial cylinder here. So we're going to have operators that are not surjective. And the way we're going to approach the gluing is very similar to how we talked about Morse gluing in the beginning of the semester, which I'm sure are all still fresh in your minds. So we'll split the J curve equation into 3. Theta plus or minus correspond to parts of the J curve equation on the top, the U plus and U minus, and theta sigma corresponds to part of the J curve equation over the pair of pants. And because and turns out theta plus or minus can be solved, but theta sigma can be solved up to a certain obstruction section. And we'll see how wiggling the gluing setup and all the pre-gluing setup, well, we can find a 0. Well, at least I'll sketch out how there is a 0 of the obstruction section. And this will correspond to an actual gluing. Okay. So let's, oh boy, I'm blasting through this lecture. So not sure how long this is going to take. Okay, so let's think about the setup. So the negative end of U plus has a cylindrical neighborhood. And we can translate U plus so that this cylindrical neighborhood starts at s equals 0. And then it goes downwards like that. Okay. And we can choose coordinates around this Rabe orbit so that U plus over the cylindrical neighborhood looks like this. It sends st to st, and then there's some perturbation in the normal direction, making it J holomorphic. There's some term, let's say term. And we have an asymptotic formula for this eta plus. It looks like some exponential decay term plus some function that depends on a function on S1. And then there's some higher order error terms. So here, gamma plus is the smallest positive eigenvalue of L of the asymptotic operator associated to the elliptic Rabe orbits. And E plus is the corresponding eigenfunction. So that's what the end of eta plus looks like. And for convention purposes, I've fixed this end. I've indicated the end by a square bracket and starts at s equals 0. I can fix similar things for the 2 positive ends at U minus. I can translate U minus so that the cylindrical neighborhoods start at s equals 0. And over each of these ends, I have a formula. So U minus and I indicate which end it is. I ranges from 1 to 2. And it looks like this. So again, it's a standard normal form that looks like ST and gamma minus I ST. And there's another normal form for what this gamma looks like. Some lambda minus I, some I think largest negative eigenvalue. And this is an eigenfunction associated to the linearized asymptotic operator. So next we imagine, so that's how we placed our U plus and U minus. Next we place our pair of pants as a branch cover of trivial cylinder. We place it so that the branch point, there's exactly one branch point, is at s equals 0 and t equals 0. And the rest of it's kind of the pair of pants. Okay. Next, we fix 2 large numbers, t plus and t minus. Please remember these 2 numbers, they're kind of important. And what we do is we translate U plus upward by T plus and U minus downwards by T minus. Okay, so in the previous picture, we had the cylindrical neighborhoods were all at 0, as I remind you here. And now we're going to translate them. I'm going to translate U plus upwards. Let me use red here, so that the cylindrical neighborhood starts at S equals to T plus. And I'm going to translate U minus downward, so that the cylindrical neighborhood starts at T minus, well, I guess minus T minus. And in the middle, I'm going to put in this pair of pants. And of course, these functions have been translated. I'll just denote them like this. And in this configuration, we do the pre-gluing. So we pre-glue a chunk of the chunk of the branch trivial cylinder with this translated copy of U plus and with this translated copy of U minus. You have to choose some cutoff functions, beta plus or beta plus or minus, and in the pre-gluing region, you're just interpolating these etas with the cutoff functions. Because this thing ST in the coordinates we've chosen, this corresponds to the trivial cylinder. Are there questions at this point? So let's make a remark about T plus and T minus. We think of their sum as the gluing as being fixed. We think of the sum of T plus and T minus is basically measuring the distance, how distance U plus and U minus are from each other. And we think of this as the gluing parameter. So, as you in the moduli space, as you move towards the boundary, the two curves get shifted farther and further apart, right? And the distance between them goes to infinity. So here we're fixing the sum of T plus and T minus, and because we're doing this at a fixed gluing parameter, but we can move them individually up and down to keep the sum constant. So there's kind of different pre-gluings depending on the choice of T plus and T minus in this fixed gluing parameter. And this is important. This will later go on to become part of our base in our obstruction bundle. Okay, next we would like to somehow deform the pre-gluing to make it J-holomorphic. So I'm going to choose sections of the normal bundle, psi plus or minus in the normal bundle of U plus or minus. And I'm going to choose a section in the normal bundle of the pair of pants. So, so here's a wiggle that's denotes psi plus. There's some wiggle here that's psi minus, and there's some intermediate wiggle that's deformations in the pair of pants. So I'm gonna patch these sections together again using cutoff function to form a big deformation over the pre-glued curve. Okay, I'm gonna apply this deformation and hit it with the J-holomorphic curve equation and see what happens. Okay. And so, of course, this is the J-holomorphic curve equation if you view them as submanifolds, but there's a version that works the same, more or less the same way. And then you do this, and I guess it's kind of like what you get is to first order is like the linearized D bar operator applied to this section. And as you would recall from the Morse case, you kind of distribute this linearized operator along these sums using the Leibniz rule. So first of all, you're going to get a differentiation on the psi plus, and then okay, I've written this in a very obscure way. Then you're going to get the beta. The betas will get differentiated into beta primes. So okay, let me say it in a less obscure way. So there's going to be, you're going to differentiate the linearized section psi plus or minus. You're going to differentiate the psi sigma, and then there's going to be cross terms from beta prime, beta prime, beta prime, beta prime, and then there's going to be some small second order nonlinear terms we're not going to write down. Okay, are there questions on this, or I should pause and explain myself? Okay, and next, so then we will separate these into 3 different equations, and so I'm going to collect some collective light terms. So if you think about it, all of these terms happen over U plus. The support of these terms is concentrated mostly over U plus. The support of these terms is concentrated over U sigma, the pair of pants, and the support of these terms is going to be concentrated over U minus. So I'm going to separate these equation into 3. I'm going to call these terms theta plus. I'm going to call these terms theta minus. I'm going to call this middle term theta sigma. Okay. And we have a J holomorphic curve equation if we set all 3 of them equal to 0. Okay. So next, I'm going to think about how to set all 3 of them equal to 0. So the thing I'm going to do is the following. So we have 3 variables, psi plus, psi minus, and psi sigma. So and these equations are not all independent of one another. So if you look here, psi plus also depends on theta plus also depends on psi sigma, and the theta minus also depends on psi sigma. So I'm gonna fix, given a fixed psi sigma, I'm gonna be able to solve theta plus or minus. And this is essentially because these 2 operators are surjective. And I can solve, and this is some kind of source term, and there's some small nonlinear terms. So I'm going to be able to solve both of the equations using a contraction mapping principle, just like the Morse case. Okay. So then I get some psi plus or minus that depends on psi sigma. And I'm going to feed it back to the middle equation. Feed it back into the middle equation, theta plus theta sigma. I'm going to try solve for that. So, oh geez, I've not left. So sorry for the bad annotation. Feed this into theta sigma. Now then this is just a function of psi sigma now, and try to solve. I'm not going to be able to do that exactly because this operator, d sigma, has a 2-dimensional co-kernel. So the argument I'm going to try to apply with the contraction mapping principle is not going to work. So what I'm going to do is I'm going to try to split this equation into 2. So let pi denote the projection to the co-kernel, of d sigma. Of d sigma. And then this equation, theta sigma equals 0, is equivalent to this. I'm going to project away all the other terms that are not in the co-kernel in the theta sigma equation, and I'm going to set this equal to 0. And I'm going to say, well, the stuff I projected away should also be equal to 0. Then the information inside theta sigma should be equivalent to being able to solve these 2 equations. Okay. Now the stuff over here I projected away. It's the stuff I projected away. The components in the co-kernel. So this equation I can solve by contraction mapping principle. Okay. And what remains is that, well, I need to look at the points where this second equation is equal to 0. And the points where the second equation is equal to 0 will correspond to an honest gluing. Are there, so I'm going to denote all the terms over here by, oh geez, I'm going to denote all the terms over here by F. And whether we or not we have a gluing is equivalent to pi of F is equal to 0 or not. Okay, this will be more likely a 40-minute talk. Okay.
What was the, I should know this, maybe I just missed the notation. What was the pi was the projection onto what again?
Pi is a projection to the co-kernel.
Okay.
Of the deformation operator corresponding to the pair of hands. Okay.
Can you repeat why the first thing was always 0?
This thing?
Like, yeah, that whole line has to be 0.
Yeah. So it has to be. Are you asking why it has to be 0 or why I can make it 0?
Why you can make it 0?
So right. So here again, so after I project out the co-kernel, this thing is now in the image of d sigma, right?
Oh, right. So you get surjectivity again, basically.
Yeah. Yeah.
Okay, cool.
So of course we want to phrase this as where this whole giant F is equal to 0. So we're gonna be able. We're first gonna phrase it a bit more cleverly, using the obstruction bundle. So instead of considering the co-kernel of d sigma, I'm gonna consider this section. This space. It's a Hom space from the co-kernel to R. It's as vector space, this is exactly the same space. Well, kind of, but I'm going to consider this. And I'm going to define an element of this. So S is an element in this space. And what it does is that it eats an element in the co-kernel and pair it with F in the L. So this pairing is the L2 pairing over the pre-glued curve. So it take an element of the co-kernel that's some vectors along the curve, and then I pair it with this F. So if you compare this with so the claim is that this thing, so a 0 of this section S, how do I say this in English? So this thing is 0 if and only if the previous obstruction vanishes. So the locations of where the obstruction vanishes exactly the zeros of this when this thing is 0, and this is almost tautologically true because you're kind of projecting away stuff, and this is measuring the stuff you projected away. Okay, so now we want to look for where this is 0. So if this seminar is any guide, you're trying to set this up as a section of obstruction bundle. So what is this base of the obstruction bundle? So recall in the pre-gluing picture, we had two parameters, t plus and t minus. We said their sum has to be fixed because that's our gluing parameter, but they're allowed to vary individually. You can make u plus closer to the origin at the cost of making u minus further away. So that's one degree of freedom we can use to try to set this thing equal to 0. Another degree of freedom is the location of the branch point of the branch cover. So previously we set it equal to S equals 0 and T equals 0. I'm going to keep it at S equals 0, but I'm going to rotate the T parameter. T is if you've forgotten, T is a coordinate that's kind of along the Rabe orbit. So I'm going to rotate the branch point in this direction. And these are the 2 degrees of freedom I'm allowed to use to try to set this obstruction equal to 0. So it turns out, Oh, that's what I just said. So the base of the obstruction bundle is this finite cylinder, and there's some bundle, and your S is this section over here. Okay. So we look for this again. We look for zeros of this section, but this section in itself is too nonlinear. There's too many terms we don't understand. So the idea is to try to throw what I'm going to try to do is try to throw away some of the terms in it that are small, and then look at the term that are remaining. Okay, I'm going to show and that's called deforming to the linearized section. I'm going to try to reason that the linearized section has a zero by wiggling these, by moving around in this obstruction bundle. And then there's some very hard argument that's saying this zero actually persists when you are in the nonlinear case. I'm not going to talk about that argument, but because that's really hard, I do the easy bits. Okay, so we can deform to a more linear section whose zeros we can actually understand. So let's recall that the section is sigma paired with f. So let's look at the f for a little moment. So so what's in it? Let's take a look. It's the eta term that comes from u plus, and the eta term that comes from u minus, and then the perturbation we added in from psi plus and psi minus, plus a bunch of nonlinear terms. Okay. So what terms are we going to throw away? We're going to throw away this term, and the nonlinear perturbations. And there are some heuristic arguments to say those terms are small. I guess I can wave my hand a little bit. The nonlinear terms are obviously small, and maybe you can choose your deformations in an epsilon ball or something. And these terms are small, and you can throw them away. So what's left is that you have this linearized f that's basically eta plus t plus eta minus t minus. And when we get to this point in the deformation, this term no longer depends on psi plus and psi minus. This is a term that you can read off by which curves are coming in your gluing parameter. So as long as when you have deformed to this, that kind of like the specifics of how you perturbed u plus and u minus are gone. It's just the information that's left in u plus and u minus. And recall, so the inner product of sigma with f0 is integrate. This is an L2 inner product over the pre-glued curve, and we can simplify this L2 inner product even further. So to compute this, you have to integrate over the entire pre-glued curve, but we can simplify that. And why can we simplify that? Because we have these normal asymptotic formulas for the eta plus and eta minus, right? That's kind of, I mentioned way back then. And so they have been translated a little bit, but they still take the same form. So eta plus, I remind you, is some e plus t, that is some eigenfunction of the asymptotic operator associated to the Rabe orbit, and here, and corresponding to this eigenvalue lambda plus. So it's basically some so e2 plus e plus t is some function on L1, and then it decays as s goes to minus infinity. Okay, that's what we said eta looks like. There is also a kind of normal form formula for sigma. So let's think about where sigma lives. It lives over this pair of pants. So it has three ends, three asymptotic ends. This end as s goes to plus infinity, and these two ends as s goes to minus infinity. And we can also write down an asymptotic formula for sigma, and it looks like this. So for sigma plus, it's basically essentially the same form. It's some eigenfunction over the asymptotic operator times some kind of exponential decay. Okay. And over the negative end, it's the same thing. It's two eigenfunctions times some exponential decay plus some error terms that are too small for us to worry about. Okay. So now with these normal forms, you can actually do the L2 pairing. And you can simplify it. You can basically get rid. So the way I understand this, you can get rid of the integration in S component. Okay, you can integrate with respect to S, and then the term that's left in your linearized section is basically the L2 integral of these eigenfunctions over S1. Okay, and the fact that you translated these curves u plus and u minus up and down by t plus and minus. Oh geez, the fact you translated u plus and minus up and down by t plus or minus is going to show up as a numerical factor that appears before the L2 pairing. Okay, so just a side note, I've absorbed the beta prime coefficients into a constant term. I've just ignored them because they're the same size anyways. So you write down this linearized section and you see, well, it's some exponential decay term that depends on t plus a pairing of sigma plus and E2 plus. And it's some exponential decay term that depends on t minus, and it's some pairing between sigma minus 1 and e minus 1 t. And there's sigma minus 2, and this is another pairing that's weighted down by another t minus. So then you try to understand, why does this thing have a 0? So already you can see some kind of the degree of freedom you had in your obstruction bundle base coming in. So t plus or t minus, well, their sums are fixed, but you can adjust them relatively. So you can change how big these two terms are by changing the relative size of t plus and t minus. Okay. But wait, there's more. So there's another further deformation to the section we have to do. We can assume that d sigma is complex linear. Okay, so we can deform this d sigma into a complex linear operator by changing without changing the number of zeros. Number of zeros. Okay. And we said the co-kernel was 2-dimensional, so we can identify the co-kernel with just C. Okay. And there's
how can we so when we're making this thing complex linear, is this throwing away nonlinear stuff, or is this specifically to do with the fact that it's like
d sigma looks like ds plus j dt plus s, right?
Mm-hmm.
I can deform this s to make it complex linear. And in particular, I'll make this s look like theta. Okay. And the advantage of passing to this deformation is that we can explicitly understand what the eigenfunctions are, because this is a very easy to solve differential equation when you fix your form of s. Okay.
But the fact that you can make the s look nice is this specifically using the ellipticity of the orbit, like that particular geometry?
The final form you can set s equal to, I think, depends on ellipticity, because you can't really change it from hyperbolic to elliptic in this deformation.
Yeah, because it'll have different signs in it.
Yeah. Okay, so I've deformed d sigma to be complex linear. So and then using some further identifications, which I didn't write out, I'm regretting a little bit now because I'm way under time. But using some further identifications, you can identify these eigenfunctions with elements as complex numbers. So something is going on here. So secretly what's happening is that Hom of the obstruction bundle is co-kernel of D sigma from R. Upon the realization that this thing is C, I can identify this with a section of Hom of C from C to C. Well, the dimension checks out. This is 2 real dimensional, and this is also 2 real dimensional. But the point I'm saying is that with some certain identifications, you can treat these as complex numbers because, well, we're taking their L2 inner product anyway. So these are just real numbers, you know. Okay. So then we can view our linearized section as these two things, these kind of exponential weight terms times a product of complex structures. Well, a product of complex numbers, sorry. Okay. So how does one set a complex number equal to 0? Well, so here, as we mentioned earlier, we can adjust the relative sizes of these two terms by messing around with t plus and t minus. But somehow to make the complex number 0, their phases have to match, right? You know, not only do the magnitude have to cancel, but the phases have to cancel. So what parameter do I have to make the relative phases of these terms cancel? The answer is rotating the what's it called? Branch point. So what rotating the branch point will do, well, E2 terms and E2 and E1 and E plus or minus, they come from U plus and U minus. They're basically asymptotic eigenvectors corresponding to U plus and U minus. So they will not change under the rotation of the what's it called? Of the branch point. But this co-kernel element is the co-kernel of D sigma. And this will depend on where the branch point is. So a little lemma is that, so we initially set our branch point at t equals 0. Suppose we change it by an angle phi, then the relative argument between sigma restricted to sigma plus and sigma minus, the sigma here, the relative argument of these two complex numbers will change by phi over, oops, let me not erase that, by phi over 2, maybe plus some epsilon. Okay. So then and the reason for this is, so you can ask, well, if I'm rotating the branch point, both ends are rotating at the same rate. Why is it there's some relative phase difference between the sigma minus and the sigma plus? And the reason essentially boils down to sigma plus is a double cover of the Rabe orbit, and sigma minus at the negative ends is a simple cover of the Rabe orbit. And if you actually write down, this part is not so hard to write down, though I regret not writing it down, is that it will boil down to the fact that these two are covered differently. And hence, when you rotate, their eigenfunctions will pick up a phase that's different. And that's the relative phase shift we're seeing over here. Okay, so then, all right, so we have, let's go back to the linearized section. We have figured out how to change the relative sizes of these terms, and we have to figure out how to change their relative phases. So therefore, there is a gluing, and in the linearized case, and you can maybe argue there's exactly one gluing, and then deformation to the nonlinear case, I'm not going to talk about because it's hard, and I end my talk here.
Sorry,
Okay.
I had to unmute myself. Okay, let's thank Yuan for the lovely talk. And let's see. Does anyone have any questions they want to ask while recorded?
I had a question. So the
Uh-huh.
T plus and T minus are like the sum is the gluing parameter,
Yeah.
but do we sort of like want the individual things to vary nicely? I mean, like we're getting wait, does that make sense?
Can you?
Like so we're getting a section and some zeros, and what the zeros will be will depend on the individual T plus and T minus, right? And not on the
Right.
sum.
There's theorems in the obstruction section bundle gluing paper that shows that somehow these as the nonlinearized gluing the nonlinear obstruction section varies continuously as you change these T plus and T minus and these branch points. Or more generally, as you vary, in the more general case, you're changing in the moduli space of branch covers. And there's very hard theorems, very well, with very long proofs that shows these varies continuously. And it shows, well, and the generic case is when you have multiple branch points. The generic point case is when the branch points are order 2, simple branch points. And you can, I think there's a theorem in there that says it is this obstruction section smooth in the generic open set where where these things are distinct and they're all simple branch points.
Okay, cool.
Yeah.
I have a question.
Yeah.
Why we want to put all the branching at s equals 0, t equals 0?
Well, you don't have to. You don't have to. So the kind of the argument I gave is kind of specially tweaked to make this picture here look good. So, but in general, you don't actually count the zeros over this setup. You actually count it over the moduli space of branch covers. There's some identification that moves it there, move the obstruction bundle here, and then you kind of do the count over there.
Is that the like truncated moduli space of branch?
Yes.
Where you have the,
well,
or it's like you have to fix the ramification points within like some distance.
so there's kind of two truncation, two things I'm aware of that's fitting of the word truncation. So there's one thing you do where you kind of somehow there's this identification. Here we did kind of we said the T plus and T minus is their sum is the gluing parameter, right? So there's an analog of doing this over here. We only make you only let the branch point vary so far away from the origin. That's one kind of truncation. And then when it comes to the actual count, if you kind of like me just briefly glance over how it's counted, they don't actually count it over this space. They find a lower dimensional space within it where all the branch points have fixed fixed S values, and they do the count over there as they're computing the degree of some map, and that's their count.
Okay, thank you.
So the way I use the word truncation, I use this word a lot. So for me, that means basically fixing T plus and T minus, and then seeing how many gluings there are for those fixed values of T plus and T minus. So we're not trying to count or even make sense of a count of the number of ends of the moduli space. We're just saying, let's fix a large value of the gluing parameter that you call R and see, cut off the moduli space there and see how many boundary points there are.
Oh, I guess advertisement for Morgan's talk. I talked about the kind of the gluing story, and next time Morgan will talk about how I kind of try to give you some intuition about why where these gluing formulas come from. Next time Morgan will talk about how they fit into ECH.
Any other questions or comments?